Thank you, Dr. Perez. As he said, I'm Stephen Pike. I'm the author of this paper with Dr. Lubomir Ribarov as my co-author. Thermodynamic assessment of a Kalina cycle as an alternative hybrid propulsion for ships. So a little bit of history. We've covered some of this in previous presentations, but we'll go over it again. CO2 emissions into the atmosphere and human activity since 1751, the beginning of the industrial age, are in excess of 1.5 trillion tons. The earliest paper linking atmospheric CO2 concentrations to global warming appears to have been published in the American Journal of Science in 1856, authored by Eunice Foote. So a little bit over 100 years after we started dramatically increasing our CO2 output into the environment, we had a study indicating that it could be a problem. And events and data since then overwhelmingly support that conclusion. Global atmospheric carbon dioxide compared to annual CO2 emissions from the beginning of the industrial age. The scale on the left there in blue is our total concentration of atmospheric carbon dioxide. And the gray line is the annual carbon dioxide emissions. And as we increased our emissions, you can see that our carbon dioxide concentration in the atmosphere continued to go up as well because we were exceeding its capacity to remove carbon dioxide. Currently, we're above 400 ppm CO2, which is higher than it's been in human history. And we reached that point in 2013 and have not gone below 400 ppm since that time. Can we actually make a difference? Well, historically, in the late 70s, we discovered that acid rain caused by sulfur oxide and nitrous oxide emissions had killed life in scores of lakes and rivers. We had Lake Placid was one of the lakes that was completely devoid of life. And we took that to heart and reduced our sulfur oxide and nitrous oxide emissions, reduced the acid rain, and our lakes and rivers have largely recovered. So you can see about 1980, the effects of the 1970 Clean Air Act had started to take effect, and we dropped our emissions dramatically. And the plot on the right is the hydrogen ion concentration, which is an indicator of pH of the rain. So the lower the hydrogen ion concentration, the less acidity in the rain. So this demonstrates that not only can we impact a system as large as the atmosphere in a detrimental way, but we can also successfully take action and the environment can recover. It's good to know. So we're now addressing the issues of greenhouse gases. Climate change, global warming are impacted by gases in the atmosphere that help us retain heat. Carbon dioxide has been recognized as a major greenhouse gas, and that's what most of the topics that we've been discussing for this conference have been about. Again, some of this will be repetitive. Shipping currently contributes to 2 to 3% of global carbon dioxide emissions. Without action, IMO studies indicate that carbon dioxide emissions projected to grow by 50 to 250% by 2050. We've seen that before. So in essence, our emissions will increase to about 10% of what our current global carbon dioxide emissions are by 2050 in the high end if we take no action. But the reason we're all here today is we're proposing that we do take action. So we're not going to encounter that scenario. Eliminating carbon-containing fuels is the ultimate goal of decarbonizing the shipping industry. We get carbon out of the combustion process, no more carbon dioxide. The recently adopted 2023 IMO greenhouse gas strategy goal is for shipping to be at net zero by or around 2050. We've had this in an earlier discussion as well. I'm not a big fan of what I call squishy goals. This is a squishy goal. It's not firm. We don't say by 2050 we're going to do this. We say by or around. So 2050, 2055. It's a goal. We're working toward it. The problem is getting all the countries to join into a firm consensus is difficult. So this was the best we could get at this time. But we're pursuing it. Item 1 of the adopted strategy is to decrease the carbon intensity of shipping through further improvement of energy efficiency for new ships. So ultimately, we want to end up at the point where we eliminate carbon-containing fuels. But in the meantime, if we can make our systems more efficient, we use less fuel to do what we're doing. We put less carbon dioxide into the atmosphere. We reduced our carbon footprint. Waste heat recovery units are a proven way to improve energy efficiency, reducing our fuel consumption and resultant CO2 emissions, allowing the environment to start to recover. Implementing waste heat recovery technologies in new and existing plants will also help mitigate what we're likely to be higher fuel costs of carbon-free fuels. As we change from fossil fuels to carbon-free fuels, there's going to be a cost involved, economic cost. Typically, they're more expensive. They're like green ammonia, gray ammonia, brown ammonia, all the different ammonia fuels, hydrogen fuel, methanol, all of those are more expensive. And some of them, methanol, for example, still have carbon, so we want to get rid of that eventually. With the increased expense, if we have more efficient plants when we get there, that will help us economically. So where does the waste heat go that we're trying to take advantage of to make our plants more efficient? It's a sand key diagram for a typical, actually not really typical, it's a fairly efficient slow-speed marine diesel plant. Notice for the 100% of the fuel energy, almost 50% is going to the shaft for our propulsion. Most waste heat recovery units only address the exhaust gas emissions. The waste heat recovery unit under discussion that we examine includes the waste heat stream from the Lubomir cooler, jacket water cooler, and the air cooler, almost doubling the amount of waste heat that we're looking at recovering. Different waste heat recovery designs. Common one is the steam ranking cycle. TS diagram on the left and a simple basic system diagram on the right. From 1 to 2, isentropic compression of the fluid. 2 to 3, isobaric heat addition or heat absorption by the fluid. 3 to 4, we're extracting work in a turbine through an expansion device isentropically. 4 to 1, we're doing isobaric heat rejection in the condenser. This is actually fairly common on older ships. I sailed on a D9 that had a waste heat recovery boiler. And once we got underway, we were going trans-Pacific. We would put the TG online and operate off of waste heat for all of our electrical needs. Unless we had a large number of reefer containers, in this case, we throw a diesel generator in. Most of the time, we had enough energy, enough waste heat was able to be recovered that we could run the electric plant just off the waste heat from the diesel engine. That's a relatively inefficient engine, older, less efficient, higher exhaust temperatures. Newer engines are much more efficient. The newer engines have 3 injectors instead of 1, common rail, computer controlled timing, so we can adjust and make the engine more efficient. That just means that the exhaust temperatures are lower, so there's less intensity in the heat, a little bit more difficult, a little bit less available for recovery. So another design is organic Rankine cycle. That's commonly used for lower intensity heat sources. Similar process. And the waste heat stream is going through this evaporator. And Similar configuration with the turbine, condenser, and a pump. And this is better for lower intensity heat sources, typically has better approach points and pinch points than a steam Rankine cycle. Our proposed waste heat recovery unit is based on the Kalina cycle. Kalina cycle is an ammonia water mixture, and it can vary anywhere from 30% ammonia less by mass fraction up to 90% or more by mass fraction. This is a simple Kalina cycle here, relatively simple, but you can see, so this allows us, because of the incline of your heat absorption and heat rejection, we have sensible heat. We can recover more heat, and we can lose less heat over the side. However, that comes at a cost of complexity. You see the system's a little bit more complex. So the heat absorption and work portions are very similar, but from the exhaust of the turbine to the inlet to the boiler, it's a little bit more complex. And it can be a better option due to the azeotropic nature. That's just describing what's happening here. And azeotropic, non-azeotropic means that you can't separate it by a distillation process. So as it evaporates, the water and ammonia are going to evaporate together. The concentration is going to stay pretty much the same, and it will condense in the same fashion. Results in additional heat being recoverable, and reduced or eliminated pinch points in approach points. So we took a Kalina cycle, configuration 11. There are numbered Kalina cycle systems that are different for different heat intensities. Kalina cycle 11 is applicable to the particular heat source that we have here. We've got the exhaust stream comes up into the superheater and evaporator section. If you recall the previous slide, we had there was no superheater section. We were just taking saturated vapor, 100% going to the turbine. Here we're running it through a superheater, the minor modification. The other difference is we're taking the freshwater cooler, instead of rejecting the heat from lube oil and charge air and jacket water and rejecting that directly to the seawater, we're recovering some of that to preheat the working fluid on its way back to the evaporator. So we took the basic unit or basic information from a Kongsberg flex engine simulator, and approximately 102 kilogram per second flow rate for the exhaust gas, 282 degrees Celsius for the exhaust gas temperature, 108 degrees Celsius coming out of the evaporator section. That's considerably lower than historically for waste heat recovery systems. And there's a couple of reasons for that. We're using much lower sulfur content fuel, so the amount of sulfuric acid formation in the exhaust is much less, and also better materials. And I wanted to use the same numbers that the Kongsberg simulation was using, so I could get a good comparison. And they were using 108 degrees, specifying lower sulfur fuels and better materials for the exhaust system. 118,200 kilowatts of heat absorbed in the exhaust. Saturated vapor liquid mix is leaving the evaporator section. You take the saturated vapor in the separator and run it over to the superheater. The saturated liquid, you recover some of that heat to preheat the working fluid coming back to the evaporator. The exhaust from the turbine, we constrain to no less than 0.85% quality. 20 degrees Celsius for the seawater. That's a little bit low for my experience. I spent a lot of time in the tropics. I would not design a plant that was based upon that low of a seawater temperature, just because it limits you to where you can go. But this was the design for the simulator, so I wanted to keep the numbers comparable. Saturated liquid coming out, and we had another 16,700 kilowatts we added when the freshwater cooler preheating the fluid coming back. So our methodology, we use engineering equation solver. It's a really impressive program. Can analyze large number of variables, and it also has built-in thermophysical properties of a large number of fluids, including the ammonia-water mixture. So that was quite helpful. We use the data from the RT Flex simulator, as I showed on the previous slide, in a loaded condition at a full head and a modified KCS11 configuration. Each major component was analyzed separately in engineering equation solver, starting with the evaporator section. We had enough equations and known values that we could solve for all the inputs and outputs. And we progressed through the entire system, component by component, until we had the complete system analyzed. And once we gathered that information, conducted each component analysis, we created a complete system analysis, a complete heat balance, and we conducted multiple analyses of the complete heat balance, starting with 0.1 mass fraction, 10% ammonia, 90% water, all the way up to 90%, actually 95%, 0.95. 90% was what seemed to be the optimal for our purposes. And that was the one that we ended up for the, in the paper, you'll see a complete heat balance with all the data that we've collected and all the calculations. What we determined was the bottom line: the system as configured can provide an additional 4,300 kilowatts electrical power, approximately 8% of the engine output. There are more kilowatts than the steam Rankine cycle that comes from simulation. So our conclusions: Kalina cycle system 11 waste heat recovery system could prove useful in increasing overall plant efficiency, result in decrease in emissions for a two-stroke roasting green diesel propulsion plant. An excellent means to reduce CO2 emissions in the short term, getting us to the point where we can start incorporating carbon-free fuels and develop more efficient plants, and that can carry over. When we start using carbon-free fuels, the greater efficiency will help us keep the costs down. And selection of the mass fraction for the ammonia is critical for optimizing the performance of this. Like I said, if you decrease the mass fraction, you end up with significantly less power produced by your turbine. As you adjust the mass fraction, you also have to adjust the operating pressures. It's quite complicated. Lots of iterations, lots of time spent conducting each analysis. And we, like I said, we end up with 90%. With a good number for producing at least as much, a little bit more, 200 kilowatts more than the simple steam Rankine cycle, at the cost of a significant increased complexity. So other Kalina system designs, there are, like I said, there's probably at least a dozen, if not more, Kalina system designs out there based upon different heat intensities and throughputs. So it's a time-consuming process, but it's worth doing. We can get, it might be better to have a saturated system going to the turbine as opposed to trying to put some superheat into the system. That will be the next step, is to do some additional analysis of different systems, see if we can improve the performance of the system. Other things to be considered, perhaps for the freshwater cooler, instead of using it to produce electrical power, we could use it in an absorption cooling system for air conditioning or refrigeration. And finally, successful development and implementation of this technology on board ships can easily translate to shoreside. So if we come up with a better mousetrap, we can build a better, bigger mousetrap for stationary planes as well. Thank you for your attention. Any questions? Yes.
I'm surprised that you got as much out of the ranking cycle for that segment. That was a water-based steam engine.
That was from the Kongsberg simulation, they had 44,000 kilowatts. We got 4,200, so.
But at this stage, it wouldn't be cost effective to go from the additional kilowatt compared between the two.
Probably not, although I'd have to look at, they had a two pressure system. Their system is also fairly complex. It wasn't as simple. It had a high pressure coming into the turbine at one point, and a medium pressure bleed into the turbine, and then a low pressure feed into the turbine. So it was not a simple Rankine cycle like I had up on the screen either. So the costs are still likely to be more for the Kalina side. So whether, how much more the bear further investigate. Correct.
And I was trying to get more about the ammonia water mixture. What was it that it did, how that thermodynamics of the water also ends up being saturated steam water to a mixture. How does that work?
It's a mixture of ammonia and water at all stages. So what happens though is in the separator, the saturated vapor coming off is a higher concentration ammonia than water. The mix is.
It's mostly an ammonia turbine. It's just the water allows for second stage recovery.
Well, partly for this system, but for other systems, there's systems that operate on 70% ammonia, and there might only be 80 to 90% ammonia going into the turbine. So the pressures and temperatures all have a very complex interrelationship, and with the ammonia water mixture, you end up having a separation process at some point in the system. And so you'll have a main cycle concentration, and then you'll have different concentrations to other points in the cycle.
Right, because the ammonia is specific here, but the water is not.
Right. Yes.
The output of the
I think it was 100 megawatts. Yeah. Oh, it's 50? 53, I'm sorry, 53 megawatts. Yeah. Oh, D9s were awesome. Any other questions? Thank you very much. As far as I know. Any questions can be emailed to me as well. I'm the corresponding author for this